The next area of thermodynamics we want to look at are the remaining laws of thermodynamics. What we get out of this is we're looking for a quantity which tells us whether a set of reactants will be able to spontaneously convert into products. That is, will a reaction proceed to the right towards products or to the left towards reactants under a given situation. We can do that already with our knowledge of equilibrium constants K, but as of now, we don't know a way to figure out K for a reaction in general without just doing the reaction and figuring out K from experiment. So some terminology first, the idea of a spontaneous process. Spontaneous is a process that happens on its own without needing to put work in. So skiing downhill here, spontaneous process, you are able to move downhill without putting any work in. Going uphill, there needs to be the input of energy as work to go up against that slope. So here are some examples of spontaneous processes. Sugar dissolving in coffee is spontaneous. We didn't need to do any external work to make that happen. Freezing and melting, right, that is spontaneous depending on the temperature. So below 0, water will freeze. Above 0, ice will melt. You notice that right at 0, that's the equilibrium state, and there the process can occur in either direction. So that's an important point as well. Lots of examples of spontaneous processes. One early way to understand a spontaneous process for a chemical reaction was this hypothesis that exothermic reactions are spontaneous and have a tendency to occur. So this is somewhat true. It turns out that highly exothermic reactions like methane reacting with oxygen to make carbon dioxide and water, the combustion of methane that happens in natural gas power plants and in your natural gas stove. This is a spontaneous process at normal conditions and does sort of happen on its own. But not every exothermic reaction is spontaneous. So if we look at something like this, water melting and turning from solid to liquid at room temperature is a spontaneous process at 25 Celsius, but that is an endothermic process. The same for something like ammonium nitrate dissolving in water. It's highly soluble. This process is spontaneous, but this is another endothermic process. So enthalpy alone doesn't predict spontaneous processes. It is true, however, that if we have an incredibly exothermic process like this, where delta H is incredibly negative, that will tend to be spontaneous at normal temperatures. But it's not the entire story. The second law of thermodynamics solves this problem of which processes are spontaneous. It states that the entropy of the universe is always increasing. The first thing we need to understand to use this is what is entropy. So we can think about it as a measure of the spreading of energy or the number of available states or number of possibilities. The slightly more casual way of understanding it as a measure of randomness or disorder is also useful to figure it out. So the more ordered a system is, the less entropy it has. The more disordered, the more entropy. And what disorder means from a technical perspective is many possible states. The variable we use for entropy is a S, and the units are joules per Kelvin. The discovery of the second law was motivated by this idea that heat can't actually be converted to work with 100% efficiency. This was very important when developing steam engines in the 1800s. Entropy, though it took a lot of work for scientists to discover, is another thermodynamic variable or state function. So it's also true that we can calculate delta S by just taking final minus initial. And so if a process increases the amount of disorder or increases the possible arrangements, it will have a positive delta S. If it decreases disorder or decreases the possible arrangements, it will have a negative delta S. The technical statement here of the second law is that the entropy of the universe increases, so delta S universe for any spontaneous process is greater than 0. Now, because the universe is made up of the system and surroundings, that means if I take delta S as the system plus delta S as the surroundings, it has to be greater than or equal to 0. An equal to 0 process is an equilibrium process, and this can occur in either direction. So unlike energy, which is conserved, entropy is not conserved in the universe. Calculate delta S universe for a process, and it's positive. This is spontaneous. If it's negative, it is non-spontaneous or spontaneous in the reverse direction. Next, let's look at the entropy of different substances. Well, Given the definition in terms of the amount of arrangements or disorder, it's no surprise that a solid has the least amount of entropy. It's the most ordered, so it has the lowest entropy. The liquid here, if we think about the arrangements, each particle here has several different arrangements as it can move around past its neighbors. So liquids have more entropy than solids because they have more possible arrangements, or we could view it as more disordered. Now, the gas, in contrast, is much, much, much more disordered. Each gas particle could be sort of anywhere in its container, and so gases have much, much more entropy than solids and liquids. That's this statement over here. To put some numbers to that, solid ice at 0 Celsius has an entropy of 41 joules per mole Kelvin. The liquid has significantly more at 63, but the gaseous form of water vapor at that same conditions has an entropy of 185.7 joules per mole Kelvin, so much, much, much higher in comparison to both the solid and the liquid. As a consequence there, in a chemical reaction, when gases are produced or consumed, since the gases have so much more entropy than anything else, we can estimate the change in entropy for a reaction by just thinking about the gases that are produced or consumed. If the products have more moles of gas, then delta S is going to be positive because delta S naught is S of the products minus S of the reactants. And so if the products have more moles of gas, the products will have more entropy and delta S will be positive. If the reactants have more moles of gas, then this will be a bigger number and delta S will be negative. If there's no change in moles, then it will be close to 0. So using this information, see if you can try the example. So for this example, we have 1 mole of gas as a reactant, 0 moles of gas as a product. So the reactants have more moles of gas, and therefore the reactants have more entropy. We can also frame it as the moles of gas decrease, so delta S is negative. Products is some small amount of entropy, let's estimate it at, say, 10, minus the reactants entropy might be, say, 210. That will give us a pretty big negative number. Some other processes that change entropy include forming a solution. In general, when we take a substance and dissolve it, we have this ordered solid state, and we replace it with this very disordered aqueous state. So something like sugar dissolving in coffee or in tea here. Many, many more arrangements here, since each of these sugar molecules can now be located anywhere within the solid. Many more arrangements, and they're much more disorder and much more entropy. Same thing with increasing temperature. When I increase temperature, I go from having the cold substance, where there are some arrangements, but each of these particles here might only be moving around a little bit when it's cold, to now when that substance is warm, each of these particles is moving around much more, and therefore there's many more possible arrangements that we could find the system in. Since entropy is final minus initial, these opposite processes, of course, would have the opposite sign of delta S. When we talk about the possible arrangements, that is another way to define the entropy. This was developed by Boltzmann and is on his tombstone. S is equal to K ln of W. So if I know the number of microstates and number of arrangements of my substance, I can calculate the entropy directly from that. The more microstates, the more entropy because of this relationship. Here's our first exercise. How does the entropy of the system change for each of the following processes? So for A, condensing water vapor, I'm thinking about the gas going to a liquid. The gas has more entropy than the liquid, and so delta S here is going to be S of the liquid minus S of the gas. Since the gas has more entropy, this is going to be a negative delta S. Forming sucrose crystals from a supersaturated solution. So this is thinking about the sucrose aqueous going to sucrose solid. Since the aqueous state has more entropy with those more possible arrangements, this is another case where delta S is going to be negative. We're going from disordered to ordered, so that's a decrease in entropy. The more disorder, the more entropy we have. Heating hydrogen gas from 60 to 80, that is the opposite. Here we're going from having a less disordered more ordered state to a less ordered state or more disordered state. So that's going to be a positive delta S. Subliming dry ice, you have to remember your prior chemistry knowledge from that part of the class. Subliming is the solid, I'm just picking water as an example, going to H2O gas, say. The solid is less disordered, the gas is more disordered, and so we're increasing disorder, increasing entropy, and that's going to be a positive change. The more disorder, the more arrangements, the more entropy we have. With that, we come to the third law of thermodynamics. This, in contrast to the first two laws, which are really earth-shattering, the third one doesn't seem as important. It's the entropy of a perfect crystal is zero at the absolute zero of temperature. Now, that might not seem incredibly important, but it is for chemistry, because what that means is when we do experiments, we can figure out the changes in entropy. What this tells us is at absolute zero, there's only one possible arrangement of the substance in that perfect solid where all the particles are locked into place, not moving around at all. At that particular point, S is equal to 0. And therefore, we can actually compare entropy on an absolute scale with any other substance. So I can actually compare the entropy of water to the entropy of iron or any other substance in the world because of this common reference point of entropy being 0 at absolute 0. Therefore, it does make sense to compare the entropy of all sorts of different substances, because we can interpret all of them in terms of what are those number of possible arrangements, or how disordered is that particular substance. Because we can make those comparisons, we can really just look at this table and learn about entropy. In the same way, if we want to learn about birds, we could look at some birds. If we want to learn about entropies, we can look at some entropies. So if I compare gaseous water to liquid, the gas has that much greater entropy. Diamond to graphite, diamond has a lower entropy than graphite. Remember, graphite has those sheets, two-dimensional sheets that can slide past each other, and so because there's some amount of arrangement between those different sheets as they slide, it has more entropy than the diamond, where each element is locked into place in its crystal structure. Helium and neon, or Br2 and I2, we can see that as we increase the mass, there's an increase in entropy. So helium to neon, more entropy. Br2 versus I2, again, similar increase in entropy as I go from Br2 gas to I2 gas. Same for methane to ethane. Here we actually see a pretty large increase. That's because ethane is a little bit bigger molecule, so in addition to being heavier, it also is able to rotate around in many different ways, and the bonds can rotate, so we have many more possible arrangements of ethane compared to methane. With those conceptual points out of the way, let's look at the standard entropy of a reaction. So delta S naught of reaction is the entropy change for the reaction at standard conditions. Gases at 1 atmosphere of partial pressure and aqueous species at 1 molar concentration. In this case, we really do need to specify this circle here. That's important. That means those standard conditions, 1 atmosphere for gases, aqueous species at 1 molar concentration. It turns out that the concentration of an aqueous species or the pressure of a gas has a large effect on entropy. The lower the pressure, the greater the entropy. The same for the concentration. The lower the concentration, the greater the entropy. So therefore, we do need to always specify what concentration we're thinking about. Because it's one of these state functions, we can do the same math we would do with enthalpy with entropy. Take the moles of each product times its value from the table, subtract off the moles of each reactant times the value from the table. And again, in this case, it's just S naught because there is that absolute scale of entropy. We normally tabulate them at 25 Celsius, but that's just for our convenience. With that new equation, what is the standard entropy change for this reaction at 25 Celsius? To solve this then, I just do products minus reactants. So when we do that, we get 2 times the entropy of CO2, the product, minus the 2 times the entropy of CO, plus the entropy of O2. Note that even though O2 is an element in its standard state, its entropy is not 0. You just have to get it out of the table. Plugging all those values in, we get negative 173.0, and the unit, remember, is joules per mole Kelvin. You can read it right out of the table. In terms of checking our answer, we do have that check that we know when the moles of gas changes, we expect a change in entropy. So here we started with 3 moles of gas as the reactant, 2 moles of gas as the product. So the products have fewer moles of gas, and therefore the product should have less entropy. That means that delta S should be negative, which matches our expectation. We can see that every gas here has roughly the same entropy. And so it's 2 times about 200 minus 3 times about 200 gives us roughly negative 200 as our entropy for this process. With that, we have our 3 laws of thermodynamics. The first law, which we covered last time, the second law, which tells us which processes are spontaneous or non-spontaneous, and the third law, which is important so that we can develop that table that contains the entropy of each substance at, say, 298 Kelvin. The one nuisance here, though, is that when we think about a spontaneous process, we need to think about both the system and the surroundings. So we're motivated, therefore, to try to think about a way to write everything just in terms of the system. We know delta S is the system, which we can do using the table that we just showed last time. We can calculate delta S of the reaction, products minus reactants. But what about the surroundings? Can we write that in terms of what's happening in the system? It turns out that we can. Delta S of the surroundings for most processes that happen in chemistry where we've got system and surroundings and we're just flowing a little bit of heat into or out of the surroundings at a given temperature, we can say that it's equal to the heat flow divided by the temperature is the entropy change of the surroundings. So when heat flows into the surroundings, because the surroundings therefore have more energy, their entropy increases. When the surroundings puts energy into our system as heat, the entropy of the surroundings decreases. So therefore we have this nice relationship. Since heat is equal to the delta H, the heat flow of the surroundings is negative the delta H of the system, all divided by the temperature T here. With this now we can write the entire entropy change of the universe just in terms of the system. So that's what we do. We plug into our second law, delta S the universe is delta S surroundings plus delta S system. Using the result from the previous slide, now everything here is in terms of the system. In theory, we could be done, but it turns out that it's convenient to work with things in units of energy. So the next step we do is we multiply both sides by negative t. When we multiply both sides by negative t, that is going to flip this inequality here, because when we multiply by a negative, the inequalities flip. And we can see that we get just delta S of the system when we multiply the negative t through here, minus t delta S right here. So the next step we do is we define one new thermodynamic variable or state function, which is the Gibbs free energy, G, which is H minus Ts. With this definition now, our entire left-hand side of the equation here is equal to delta G. So we now actually have what we're after. For any spontaneous process, we have that delta G needs to be less than 0. That's the criteria that the entropy of the universe will increase. And that's what's going to tell us which processes are spontaneous in the forward direction or conversely spontaneous in the reverse direction. So this is the key result we've been looking for. For a process like A goes to B, we can calculate delta G. Really, if it's a reaction, we're actually going to be calling this delta G of reaction. In the same way we had delta H of reaction and delta S of reaction. If delta G is less than 0, the reaction is spontaneous in the forward direction, proceeds right towards products. Remember, that's the case where Q is less than K from earlier in the semester. If delta G is positive or greater than 0, it's non-spontaneous or spontaneous in the reverse direction. That's the case where Q is greater than K. The reaction proceeds in the reverse direction. If delta G is equal to 0, that's the equilibrium condition according to thermodynamics, and that's equilibrium where Q is equal to K. So if you want to answer a question about this, you can always go back and apply your Q versus K analysis if needed or desired, but delta G, the sign of delta G, works in more scenarios for things where we don't actually even have a reaction quotient Q. Delta G, since it has this definition in terms of delta S and delta H, also gives us the meaning behind why a process is spontaneous, which we'll investigate on the next couple of slides. Here's the formal definition of the free energy change of a reaction. Delta G reaction, and at standard state, that's the circle. The circle there is important because the entropy of each substance depends strongly on pressure and concentration. So we can determine this using the delta G of formation, just like we have a delta H of formation. It's an energy, and so that reference point of the elements in their standard states still applies. So delta G of formation for an element in its standard state is 0. And this will let us get delta G of reaction from our data table. Now, when we're thinking about this standard state, that's this condition where all the gases have a partial pressure of 1 atmosphere. All the aqueous species have a 1 molar concentration. In that case, remember when we get our Q is equal to products over reactants, since every term here is going to be 1, it's 1 to a bunch of different powers, which is still 1. The standard state condition is where Q is equal to 1. We can calculate delta G of reaction using the same products minus reactants times their moles formula that applies to delta H and delta S. Given that, take a minute to try this example. Here's the solution to A. We're going to do the normal products minus reactants. So the products here, 12 CO2 gas and 6 H2O liquid. So 12, negative 394.4, using the value for CO2 gas, plus 6, negative 237.1, minus C6H6 is 2 times 124.5. Then O2 isn't given in our table here, but remember that it's an element in its standard state, so it has a delta G of formation of 0, just like it has a delta H of formation of 0. Final answer then is negative 6404.4, and the unit is right off of the table, kilojoules per mole of reaction. Using that, is the reaction spontaneous at 25 Celsius at standard state conditions? That means the partial pressures of each gas are 1 atmosphere of concentration. So in this case, using our key knowledge from the last slide, yes, since delta G is negative, this is spontaneous in the forward direction. That's maybe not a surprise. This reaction is a combustion of benzene. This is a reaction that goes basically completely to products. If we started like this with a little bit of reactants and products, 1 atmosphere of pressure of each gas, and we put a spark in here, the O2 and benzene would burn, and we would get to nearly all products. Let's say we weren't given the delta G of formation. We could get delta G from delta H and delta S individually using the definition of delta G. Another thing off your equation sheet, delta G is equal to delta H minus T delta S. That's really nice because of 2 reasons. One, this would let you easily see how delta G would change at different temperatures, so we could just plug in a different temperature and get a good estimate for how delta G varies with temperature. The other reason is since delta G depends on 2 factors, both the enthalpy, which is related to sort of the strengths of bonds in reactants and products, and the entropy, which side has more disorder or more possible arrangements, we can understand the why behind a reaction is favored by breaking it down into these 2 factors. In this case, if we do that, we see that delta H is incredibly, incredibly negative. And if we look at the value of delta G, it's almost the exact same as that value of delta H. Delta H is negative 6534 kilojoules per mole. Delta G is negative 6404 kilojoules per mole. While the entropy change is slightly negative, that is disfavorable because when you take this equation here, when you put a negative number in here and do minus T times a negative number, that makes delta G more positive or less favorable. But in this case, it's that incredibly exothermic part of the reaction. Just so much energy is released when you form the strong bonds in CO2 and liquid water. That's why this reaction favors products and why it's a spontaneous process, is forming those very strong bonds. Note that when you do this mathematically here, you do always need to adjust for units. Delta S comes out in joules per Kelvin, and delta H comes out in kilojoules, just kilojoules. So when you convert, you will have to account for that. Again, in this case, the conversion factor is here, going from joules per Kelvin to kilojoules per Kelvin, negative 0.438 kilojoules per Kelvin. And then you can multiply the temp by the temperature and make everything match out correctly. Here's the next example. I'll show the solution on the next slide. In this case, since I'm given delta H naught and delta S naught, I can use the definition of delta G. Delta G naught of reaction is equal to delta H naught of reaction minus T delta S naught of reaction right off the equation sheet. So plugging in, I'll make sure all my units match. Negative 851.5 kilojoules per mole for delta H, minus my T is 298 Kelvin. And my delta S, this is where I want to make the units match. Since I have kilojoules here, I'll convert this to kilojoules. So negative 38.5. And then converting to kilojoules is times 1 kilojoule per 1,000 joules. Gives me, moving the decimal place 3 places left, negative 0.0385 kilojoules per mole Kelvin. Again, would be perfectly reasonable to also just convert joules to kilojoules to joules here. Final answer then is negative 840.0. The unit is kilojoules per mole up here. To check the answer, that makes sense because we had this very large negative number, and we subtracted off. This is negative times a negative, so this term comes up positive, so it goes from being negative 850 to a little bit larger because we added this positive term onto it. So from negative 851.5 to negative 840. Again, the other thing to do would be convert the other direction. That's nice because it sort of goes the same way as we did earlier in the semester, where, remember, we have kilo. That prefix means 10 to the 3, so we can just replace that with times 10 to the 3. You can type that right into your calculator, just like you would have done back in earlier in the semester, 851.5 E3. And that's a nice way to get 2 base SI units. Just replace the prefix with its meaning. In terms of this value, this is a very large negative number. We can see that for this reaction, since it's so exothermic, it releases so much energy, this is a highly favorable process. Even though it's slightly disfavorable from the perspective of entropy, this overwhelmingly large negative delta H wins out and makes this process favored at standard conditions. So these two factors determine whether a reaction favors reactants or products. The first is the enthalpy. We can see that since what we want to make a reaction favored is for delta G to be negative here, we can do that by having a negative delta H, which means an exothermic process. The more exothermic a process is, the better from the perspective of getting products or making a process favorable. Remember that the more exothermic something it is, that's going to be the stronger bonds in sort of the products, or whichever the side that's favored is going to have the stronger bonds. So one way to make a process favorable is form really strong bonds. That'll have a tendency to cause it to occur. If we look at this equation here, since this second term depends on T, when we plug in T is equal to 0, we have that just delta G is equal to delta H. So at 0, absolute 0, or at any sort of relatively low temperature, the only thing that matters is who is more stable, who has lower enthalpy or stronger bonds. Now, as the temperature gets higher and higher, eventually the term that dominates is the other one, entropy. At very high temperatures, what wins out is the side that is more disordered or has more possible arrangements. Again, we can see that for this delta S term, to make delta G negative, we want more entropy. So a positive delta S makes this reaction favorable, and this factor wins out at high temperatures. So the summary breakdown is right here. If the signs are the same, then we have the case where at one set of conditions, one side of the reaction is favored, at the other set of conditions, the other side is favored. So if you take a classic example like H2O solid going to H2O liquid, in this case, if we think about the energy or the enthalpy, the solid is lower in energy than the liquid. The solid is the most stable possible arrangement of the molecules, and so this reaction has a delta H that's positive. When we think about the delta S, well, solids have lower entropy than liquids. Liquids have that more disorder, and so the delta S for this reaction is also going to be positive. As a result, therefore, it's no surprise that at the lowest temperatures, as we go down to absolute 0 or below 0 Celsius, the solid is favored. That's because of the enthalpy term here. At low temperatures, this reaction doesn't occur solid to liquid because of that positive sign of delta H. As we go to higher temperatures, though, eventually that minus T delta S term will start to win out, and eventually we'll get to the point where the liquid is favored because the liquid is more disordered. As the temperature gets higher and higher, we always favored the most disordered and most arrangements possible side of the reaction. So far, what we've written down has only been delta G naught here. This is delta G at standard state conditions. But of course, we can calculate delta G at non-standard conditions. We already referenced that when we talked about the fact that delta G really goes along with our K versus Q content from exam 3, just providing a more solid thermodynamic understanding of why something is going to proceed towards products or towards reactants. So here is the equation that says this is delta G under sort of any conditions, how it depends on delta G under standard conditions, and the reaction quotient Q for a given reaction. When we write Q for this, we're going to use gases in atmospheres and aqueous species in molarity. This also explains our variable we used here, which is called free energy. Delta G is called the Gibbs free energy because delta G is the available work from a chemical process. So if I calculate delta G under some conditions, that tells me what's the most work I could do by running that particular chemical reaction. Take a minute to try this exercise at standard conditions. Is the reaction spontaneous? Well, at standard conditions, that's that circle. So at standard conditions, is the reaction spontaneous? Well, delta G is negative, so yes, it is spontaneous. We could say the forward reaction is spontaneous at standard conditions because delta G is negative. For predict the sign of delta S, that depends on those moles of gases. We have 4 moles of gases as reactants, 2 moles of gases as products, and so therefore the reactants are going to have more entropy, and when we do products minus reactants, we're going to have, a small entropy minus a large entropy is going to be a negative answer. It's actually going to be the exact same sign as just taking the moles of gas and calculating delta moles of gas. It'll have the same sign as the delta S. C, is the reaction spontaneous with these partial pressures? Now, to do that, we need to apply that new equation. Delta G is delta G naught plus RT ln of Q. So to do this, we're going to need Q. We have delta G naught here. That we know. We know R, the ideal gas constant. T, temperature has to be in Kelvin. Q, we have to write down for this reaction, products to the coefficients over reactants to the coefficients. We can write that in terms of concentration units. Technically, we are going to plug in pressure units, so maybe it's better to write it as PNH3 squared over PN2 times PH2 cubed. Either way, when you write it down, that's fine, as long as you plug in the values in atmospheres there. When we solve that, we get Q is equal to 1.85 times 10 to the 7th. Then we can plug into delta G. When we plug all of that in, here's the result. Remember to use joules per mole here. We can do the same trick of replacing the prefix with the unit here, times 10 to the 3, to go from kilojoules to joules. That'll match our value of R, which is also in joules per mole Kelvin. Then for delta G, we get 7,460 joules per mole. Since that delta G is positive, the reaction is not spontaneous, and in fact, the reverse reaction is going to be spontaneous, right? That's the case where the reaction is going to go left towards reactants. And we can see here, though, that even at standard conditions, this reaction is spontaneous in the forward directions. That's the case where we have a Q of 1 atmosphere for all these gas pressures. In that case, the reaction would proceed forward towards products. Here now, though, Q is too big, and the reaction is going to go back to the left towards reactants. For our bonus, what is delta G naught F for NH3? The idea here is that this is the formation reaction, but the formation reaction is just forming 1 mole of NH3. So this is actually, if I take this reaction and multiply it by 1/2, I'm going to get the delta G naught of formation reaction for NH3 gas, and so it's actually just going to be negative 17 kilojoules per mole is our delta G naught for NH3 using Hess's law, taking this whole reaction and multiplying by 1/2. When we do that, we can do that enthalpy arithmetic for enthalpy, entropy, free energy. All of our different variables scale by that same factor. Our final new equation is this. This applies our two equilibria criteria to this equation. So we have delta G is delta G naught plus RT ln of Q. At equilibrium, though, we know delta G has to be equal to 0, and Q is equal to the equilibrium constant K. So when we plug that in, we have 0 is equal to delta G naught plus RT ln of K. That gives us these two results. Delta G naught is equal to negative RT ln of K, or K is equal to e to the negative delta G naught over RT. This is actually now our sort of definition of the equilibrium constant. Earlier on in the class, we said it should be defined without units, and that's because of this. When we look at this here, our equilibrium constant is in fact unitless because this e to the negative delta G naught over RT is a unitless number. And so this lets us determine equilibrium constants in many different reactions or calculate the K from our table of thermodynamic data. Really powerful, so that we don't need to just measure each reaction on its own. We can have a table of thermodynamic data and now know what the equilibrium constant is going to be for any reaction we can imagine using those components. So here's the exercise. What is the equilibrium constant for this reaction given delta G naught? The equation off the equation sheet, K is e to the negative delta G naught over RT. Now we just need to make sure all our units match properly. So K is equal to e to the negative. I have kilojoules here. I'm going to just convert that to joules. So negative 141.77 times 10 to the third joules per mole. Divide that by R, 8.314 joules per mole Kelvin, times T, 298 Kelvin. So all the kelvins cancel, the joules per mole also cancel, and we get our final answer. I initially mixed my negative here. There's a negative outside the delta G, and then delta G is negative, so that negative times a negative makes it positive. Final value of K is 7.1 times 10 to the 24. So that's a gigantic value of K. That's because this is a reaction that strongly favors products with that very large negative delta G. Remember our value of K, reactants on the left, products on the right. K equals 1 is sort of that dividing line where it's sort of the rough mix of equal amounts of reactants and products. When K gets to be this very large number, the reaction favors products by a large amount. So K is a very large number and delta G is a very negative number. The more negative delta G naught is, the more the reaction favors products. In the same way that a larger value of K favors products more. This shows some of that same information about delta G versus delta G naught. If you look at a situation like this, if I start out with pure reactants, I can minimize my free energy by going to the right towards products. Eventually, I reach the minimum free energy. That's this point right here where we're at equilibrium with a certain amount of reactants and products. This is my equilibrium state, and I know I'm at equilibrium because any change I make would increase my free energy. I can only do things that decrease free energy, which is equivalent to doing things that can increase the entropy of the universe. So I sit here at this minimum free energy. Same for this type of reaction. Note that what delta G naught tells me is whether a reaction favors reactants or products here. In this case, delta G naught is negative, means the reaction favors products a bit. Delta G naught is positive, means the reaction favors reactants a little bit. So the equilibrium position is over here a little bit to the left. Now, whether a reaction actually proceeds right towards products or left towards reactants depends on what mixture I start with. So if I start here with a smaller Q, I can go to the right towards products. If I start here with a larger Q, I can go back left towards reactants, and so forth. Here's an application to biochemistry and biology. If I'm trying to form a protein by taking aniline and glycine, two of my amino acids, to form this dipeptide, this reaction actually has a positive delta G naught. So on its own, this reaction isn't going to proceed very far towards products, and I'm not going to have a very successful synthesis of this protein. What the body is able to do is to couple this reaction with the use of enzymes to this reaction of ATP going to ADP. And when we combine these reactions together, now we get delta G naught is negative, and we're able to get a significant amount of this product being formed by coupling these two reactions together carefully. So we can sort of view it as the energy that's released when we go from ATP to ADP is being used to drive this reaction forward. This reaction on its own wouldn't be successful, but when we add in this ATP to ADP step, we're able to successfully synthesize the polypeptide. With that, we conclude our thermodynamics section of the course. We have our laws of thermodynamics here, including the new concepts of entropy, which always increases in any spontaneous process, so delta S in the universe always increases. Our new variable entropy, which we use S for, in units of joules per mole Kelvin, if we're thinking about a chemical substance. Remember, that is related to the number of arrangements, so more arrangements, more disorder is equal to more entropy. We can qualitatively understand the entropy changes in different processes, with liquids having more entropy than solids, gases having much more entropy than liquids. More moles of gas will give me a bigger entropy, so we can use that to determine delta S of a reaction in a qualitative way. We also have these additional facts. When we mix two substances, the entropy increases due to being more disordered, more arrangements. At low temperature, according to our Gibbs energy as defined over here, delta H minus T delta S, at low temperature, we need to favor the lower enthalpy side of the reaction, basically the side that's lower in energy, more stable, more bonding, or stronger intermolecular forces. At high temperatures, in contrast, we're going to favor the side that's more disordered and has more possible arrangements. For S, we can determine delta S using our data table of standard entropies. Once we have S along with H, which we dealt with in the previous class, we can now do that to look at delta G for a reaction. If delta G is negative, the forward reaction is spontaneous. If delta G is positive, the reverse reaction is spontaneous. And when delta G is equal to 0, we're already at equilibrium. So delta G, just like S and H, we can do products minus reactants. Note, if we're doing products minus reactants, that's only going to work for off the data table at 298 Kelvin. If we want to go to a different temperature, we're going to need to use the individual delta H and delta S. So we can do delta H minus T delta S and use this to see how delta G changes with temperature. At equilibrium, we know that delta G has to be equal to 0, so this lets us estimate the melting point or boiling point of a substance using the delta H and the delta S. Again, same concepts as before. At low temperature, we go to the lower enthalpy or energy side. At high temperatures, we favor the higher entropy side of the reaction. Standard state is really important for our entropy especially, and so therefore when we have delta G naught is quite different than delta G. Delta G naught is delta G at standard state conditions, where Q is equal to 1 for each reaction. On the other hand, when we go to different concentrations, delta G at these new conditions is equal to delta G naught plus RT ln of Q. So depending on what Q is for a particular reaction, the reaction quotient, we can get a different sign of delta G, which corresponds with what we already knew from equilibrium. If Q is less than K, the forward reaction is spontaneous and the reaction proceeds to the right. That's the case when delta G is negative. When delta G is positive, the reverse reaction is spontaneous, or the reaction proceeds left towards reactants. When delta G is equal to 0, that's our equilibrium criteria, the same as Q and K being equal, and we know that we're at equilibrium only in that one case. The final link between equilibrium and thermodynamics is this equation right here. Delta G naught is equal to minus RT ln of K, or the other form, E is to the negative delta G naught over RT is equal to K. That lets us define the equilibrium constant of a reaction just using this thermodynamic data, which is incredibly powerful so that we don't need to perform the reaction to figure out what the equilibrium constant is. We just use the information from our table and can get a good understanding of the equilibrium position of any reaction.